Okay, good afternoon. This is about तुम्हाला. Okay, so we again start our chapter is crystal field theory. So in last lecture we saw the splitting of d orbitals in strong and weak field condition. After that we are going to discuss the evidences for CFSE. You already calculate CFSE for D1 to D10 system in strong and weak field. So what is the evidence? Is it the really crystal field is exist, crystal field stabilization energies exist or not? So for that we consider two energies of complexes. Every complex has different kind of energy, and in that here we consider two energy, lattice energy and hydration energy. So what is the meaning of lattice energy? When one mole of lattice is formed, that time the energy which is evolved during the formation of one mole of substance in a crystal lattice, that time the energy is the lattice energy. Second one is hydration energy. When the cation, when the metal ion interact with or with the water molecules, so that time it form the water complex. So the energy which is evolved during this is the hydration energy. So basically we consider here calcium, means calcium is the last element of S block in a first transition series. After that start the scandium, titanium, vanadium, chromium up to zinc. If we consider the lattice energy of these elements from calcium to zinc or scandium to zinc, we observe this type of trend. This is the trend. Okay, so it is a regular trend is observed for the lattice energy. Same thing for the hydration energy also. When we consider from scandium to zinc, we observe the lattice or hydration energy, their points are plotted on the straight line. But here what happened? This type of two curves are observed. Here the point first dot or round, if we consider, which is on the line, here also one of the spot on the line, the last spot also on the line. Why only three spots are spotted on the line and remainings are above the lines? Here also remainings are above the line. So here it is the D0 system. It is the D0 system. Calcium has D0 system because there is no D electron. Calcium belongs from the S block. Here it is a manganese. Manganese has D5 system. Manganese has D5 system if we consider the plus 2 oxidation state. Here zinc 2 plus also has D10 oxidation, D10 system. So D0, D5 and D10 in a weak field, if we consider in a which field? Weak field. So these three system has 0 CFSE. If you we already calculate the CFSE is 0. Here for D0 always CFSE is 0 because there is no D electron. D5 in a weak field. You know the splitting of D5 in a weak field. If here 5 electrons, so 1, 2, 3, 4, 5 means D5 has T2G3 and Eg2 electronic configuration. So here minus 12 beta plus 12 beta, the CFS is the 0. Same thing for D10 system also. Same thing for the D10 system also. Means D0, D5 and D10 in a weak field has 0 CFSE. So that's why if we observe the lattice energy increases regularly. It is increases regularly, and which is the all the points are plotted on the straight line. But for D0, D5, D10, these three system their plots also comes or pointed on the straight line. That means here there is no CFSE, that's why only lattice energy is there. This indicates points are plotted on the straight line. Why the remaining? Means other than D0, D5 and D10, all other systems has the points of lattice energy above the trend, above the straight line. Why? Because of in addition with lattice energy there is a CFSE, and due to introduction of CFSE in total energy, this point we expected here if I just circle here, hollow circle, what we expect? We expect here, but actually we expect here for the lattice energy, but the point comes here. Why this happen? Because of with this there is a introduction of CFSE, that's why the point comes here. We expect for another one, next one is here, but the actual point is here. For the next one again here, but actually is here. So the trend is observed. It is a increases then decreases, increases then decreases, means the energies of other than D0, D5 and D10 systems are above the straight line. That means there is a presence of additional energy. And which is the additional energy? The energy is CFSE. The energy is CFSE. Same thing here. If you consider hydration energy, same thing is observed. We expect the hydration energy points on the straight line here, but actually what happened? The points are here. We expect here at this point, at this point. Okay, but experimentally, what is the observation? The point comes and this here. So why this happen? In addition of hydration energy, there is the introduction of CFSE. That's why the value of CFSE slightly increases, and when value is increases, the points are pointed on the plotted on the above the straight line. So they are plotted above the straight line. But for this D0 system, for D5 system and for D10 system, there is no CFSE, additional CFSE. That means their points of hydration energy as well as lattice energy comes on the straight line. These energies indicates there is a presence of CFSE. There is a presence of CFSE. So those system has zero CFSE, their total energy is equal to actual hydration energy or lattice energy. But those has some CFSE, their energy is hydration energy plus CFSE. So that's why this type of curves are observed. So this is all about the presence of CFSE, and this is the important evidence to find is it CFSE really exist or not. Okay. So next point we are going to discuss here the crystal field spectra and measurement of 10 dq value. So crystal field spectra and measurement of 10 dq value, measurement of 10 dq or delta node. Okay, so what is the meaning of this? So crystal field spectra and measurement of 10 dq value. We already discussed the splitting of d orbital, and we saw there is a presence of electron in lower energy orbital as well as in higher energy orbital. But in some cases there is a presence of electrons only in a lower energy orbital. Suppose any lower energy orbital has, suppose we consider this type of splitting in octahedral field, and there is a some electron. Suppose one of the electron is present here, one of the electron is present here. So it is possible this electron goes in an excited state. So next what happen? There is a excitation. When it excited goes in excited state, we get this is okay. So to jump electron from lower energy orbital to higher energy orbital, there is a need of energy. There is a need of energy, and you already know this is the total considered as a 10 dq. This is considered as a 10 dq. So depends on metal ion, depends on availability of electrons, how many electrons are here, that will decide how much energy to be required to promote electron from ground level to excited level. This phenomena is the absorption. This is the absorption. So absorption energy to be required to promote the electron from higher energy state to lower energy state to higher energy state. So using this spectra we can calculate the 10 dq value. So crystal field spectra and measurement of 10 dq value. So we're going to discuss here with the example. Suppose, what is this 10 dq spectra? What is the meaning of 10 dq spectra? So here, how we get the spectra? So basically here is the frequency in a centimeter. So frequency is considered per centimeter, and there is a molar absorption. Here is a molar absorption. Okay, so molar absorption versus frequency, which is considered in a per centimeter. So suppose for particular point we get this type of spectra. We get this type of spectra here. So what is the meaning of that? What is the meaning of that? Here is the molar absorption. So in given spectra, one of the peak to be considered, this is the peak highest, this is not, it is just considered here. So this peak Hymns particular value is here. Suppose we consider here 10,000 per centimeter, here 20,000, here 30,000 per centimeter. So that means a particular complex has higher molar absorptivity here. This is the frequency. This is the highest absorption frequency. So if we know the absorption frequency, using absorption frequency we can calculate the 10 dq value, actually measurement of 10 dq value, and in that point we are going to discuss it. So for that we consider the simple example is titanium H2O6 3+. Titanium H2O6 3+, it is considered, and if we calculate if you draw the splitting of this, here titanium has 22 atomic number, electronic configuration AR, then 3D 4s2 3d2. Okay, so +3 oxidation state, that means here just 19 electrons are remaining. So you can write AR 3d1 4s0. So in a D, how many electrons? 1 electron. So you can split this. Here is a T2G, here is a EG, T2G, here how many electrons? 1 electron. This electron after the splitting enter into always T2G. This total is the 10 dq value. This is equal to, so when this electron is promoted from T2G to EG in a next set, so energy required to promote, again here is a 10 dq value, here is the 10 dq value, but this 10 dq value has given, it is a 20,400 per centimeter. The 10 dq value, it is the absorption frequency is given to you. How much? 20,400 per centimeter frequency is given, means this is the frequency which is required to promote electron from T2G to EG. So this is the absorption band, this is the absorption frequency, absorption band. If we know this value, we can calculate what is the 10 dq value, because 10 dq value it is equal to this one, but actually it is a absorption band, it is not a 10 dq value. So once we know the 10 dq value, absorption band, we can calculate the 10 dq value for any complexes. How we calculate it? How we calculate it? For this example we consider, so here the frequency is given 20,400 per centimeter. It is a wave number. It is the wave number. Actually unit of frequency is always in hertz, but when it is in a centimeter given, it is considered as a wave number. So you know here energy is equal to 10 dq value. Energy is equal to 10 dq value. Energy किती असते? ही 10 dq value एवढी त्याची एनर्जी असते, ऑलरेडी दिलेलं आहे स्पेक्ट्रा मध्ये. and you know what is the energy? Energy is equal to h mu. H is the Planck constant, v is the frequency, but you know mu is equal to frequency is equal to c mu bar, means c is the velocity and mu bar is the wave number. It is the wave number. So using velocity of light and wave number means absorption frequency. Absorption is given, we can calculate the frequency. If we calculate the frequency, we have the Planck constant. Using this we can calculate the energy. So the total energy is equal to 10 dq we can calculate. So here we introduce, so here energy is equal to 10 dq, also is equal to h mu, it is equal to h c mu bar. Okay, so we have the value. What is the value of Planck constant? 6.024 into 10 raised to minus 24. So 6.06 6.624 into 10 raised to minus 34 is the Planck constant, which is given in joule, per molecule, into this is the what, it is the wave number which is considered in a per centimeter. That's why here we also consider the velocity of light also in a centimeter, and it is the 3 into 10 raised to minus 8 meter and 3 into 10 raised to minus 3 into 10 raised to 10 centimeter. So C is equal to 3 into 10 raised to 8 meter, 3 into 10 raised to 10 centimeter. So use here, what is the value of C? If the wave number which is considered frequency, which is we are going to calculate in a per centimeter, that's why we consider in a centimeter. So 3 into 10 raised to 10 into wave number is given to you, how much? It is a 20,400. 20,400 is given. If we calculate this one, the answer is 4.054 into 10 raised to minus 19. 10 raised to minus 19 joule per molecule. Because of here the Planck constant which is in a joule, the velocity of light in a centimeter, and the wave number which is also given in centimeter. That's why total energy which is considered in a joule. So we calculate the energy in a joule. So find out the total number. So if there is a joule per molecule, once we know this, we can calculate this energy per mole. It is the molecules. Okay, so you know the total energy always for the 1 mole is equal to Avogadro's number. It is a 6.020. so multiply this, so energy into Avogadro's number. So energy which is converted into per mole, it is converted into per mole. So here 4.054 into 10 raised to minus 19 into 6.023 into 10 raised to 23. So 6.023 into 10 raised to 23 is the Avogadro's number. It is a joule per mole, because which is considered here joule per mole. So the answer is, it is the 244.2 kilojoule. 244.2 kilojoule. Okay, and when it energy always consider in a kilocalorie and calorie, when you converts into this, it is the 58.35 kilocalorie per mole. Okay, so 1 kilojoule is equal to so here you just remember 1 kilocalorie is equal to 4.18 kilojoule. 1 kilocalorie is equal to 4.18. So just the answer which is coming after calculate into energy convert into per mole, just divide by this one by 4.18. कितीने डिवाइड करायचे? 4.18 ने याला डिवाइड करायचं, जे आन्सर येईल ते असेल किलो कॅलरी पर मोल मध्ये असेल. आणि हे आन्सर काढल्यानंतर सो डेल्टा नॉट इज इक्वल टू द एनर्जी 244.2 kilojoule or 58.35 kilocalorie. This is the 10 dq value. This is the 10 dq value we consider as a 10 dq value. Similarly, we are going to solve the another problem. So for the complex which is given CrCl6 3 minus, and the absorption frequency is given, the complex shows DD transition and the ion at the 13,640 per centimeter. Okay, so same we can calculate. So energy is equal to 10 dq. It is also is equal to h mu, or also equal to h c mu bar. Okay, so here we just put the all the value, we put the Planck constant 6.624 into 10 raised to minus 34 into the velocity which is considered in a centimeters, it was 3 into 10 raised to 10 into what is the wave number is given, it is absorption band is given 13,640. Okay, just put all the values and the answer is 2.710 into 10 raised to minus 19 into 10 raised to minus 90 joule per molecule. So convert this into number of moles, convert into 1 mole. And you know the 1 mole is equal to how much now? It is a 6.023 into 10 raised to 23. It is a 10 raised to 23. It is the Avogadro's number. So multiply, simply converts into mole by multiplying Avogadro's number. So 2.710 into 10 raised to minus 19 into 6.023 into 10 raised to 23. So the answer is, it is a 163.26 kilojoule per mole. Kilojoule per mole. So simple, we want to convert into kilocalorie. So multiply this one by 4.18. So here 163.26 divided by 4.18. The answer is 39.02. So 39.02, it is a kilocalorie per mole. Kilocalorie per mole. So this is the, or it is a 10 dq. It is the 10 dq value. So 10 dq value means the energy which is calculated using the absorption spectra. So once we have the absorption spectra, we can calculate. So for that, simply the energy is equal to 10 dq value. You know energy is equal to h mu, means Planck constant into frequency. How to calculate frequency? It is the velocity into wave number. So it is a h c mu bar. We have the Planck constant value 6.624 into 10 raised to minus 34. We have the value of velocity of light. It is a 3 into 10 raised to 10 because it is considered in a centimeter. And this value is given to you. Others are constant. So just change this value, the value which is given to you. Okay, whatever value is given to you here, you just put here to find the answer. The answer which is in a joule per molecule, convert this into per mole by simple multiplying by the Avogadro's number. It is a 6.023 into 10 raised to 23. So after that we get the value which is in a per mole. Okay, so kilojoule per mole which is converted. So simply if we do this multiplication, 2.710 10 raised to minus 19 into 6.023 10 raised to 23. So you get the answer. It is 1,63,223. It is the joule, because here the value which are given in joule. So you directly not get this value. You get, it is the value which is given is, after this multiplication, 1,63223.3. Okay, so it is converts into joule. So divide here by 1000. Divide here by 1000. If we divide by 1000, we get 163.22 or 22, whatever, it depends on your calculation. So you get value into kilojoule. First of all, here you get the value into joule. Then after it converts into kilojoule by multiplying this value by 1000, you get the value into kilojoule. It is the kilojoule, then you converts into kilocalorie. Simple, divide by here 4.18, 4.18 याला जर divide केलं कारण की 1 kilocalorie almost equal to 4.18 kilojoule. So kilojoule is higher value than kilocalorie, so you get the answer into kilocalorie. So this is a 10 dq value, this is a 10 dq value you can calculate. So this way you solve the which is number of problem which is given in exercise, you solve all the exercise using same way. So in next lecture we're going to discuss the factors affecting on 10 dq value. Means 10 dq value is vary by the complexes. So every complex has different kind of value, so the value two complexes having something differences, so y shows different value. So it depends on the factor which are introduced. So for that the number of factor means this is the, in some cases metal ion has same oxidation state, but it is possible the different nature of ligand. Sometimes ligand is same, different metal ion is present, so this is another case. And third, the metal ion having same ligands, but it is possible one of the metal belongs from the first transition series, another metal maybe belongs from second transition series. So first transition series, second transition series, third transition series. So again the position of the metal also decide the 10 dq value, because the orbital change their energy and they change their size. So it depends on repulsion and it depends on the splitting. So how splitting is powerful or not, it depends on number of factors we will discuss in next lecture. So in today's point we only discuss the what is the evidence, and that's after that we discussed the 10 dq value how to calculate using the spectral information. If you have we have the spectral information, we have the frequency, we have the absorption band, we can calculate the 10 dq value here. Okay, so this is the extension. In higher condition we can calculate number of parameters using this crystal field data. So but this is not included in syllabus, so we stop here today. We discuss some other factors affecting in a next lecture.